Hi everyone. So now I'm going to give you an example. Prove the following statement. 3 to the n is odd for all n in the naturals. So if you want, so I personally don't use this notation when I'm, oopsie daisies, meant to choose the highlighter. I don't personally use this notation when I'm doing induction proofs, but if that makes more sense to you, then ride with it. I'm personally just going to keep writing things like out, but you can do either way. Just remember, it's never an equal sign because it doesn't make any sense for a statement to equal something. Like it's this quantifier is defined as a statement. Okay? All right. So hopefully you remember there's 3 steps to induction. Okay? So my first one is base case. Who is my base case here? Well, what's the lowest number that I can grab from here? It's 1. So let n equal 1. Then 3 to the 1 equals 3 is odd. Well, let's split it up. We know 3 is odd. And then just an extra flair, since 3 equals 2 plus 1. So 2 times 1 plus 1. Remember, that's our definition of odd. It's 2 times an integer plus 1, or minus 1. Okay, so we could have also said 4 minus 1. All right, so now we're done with that one, inductive hypothesis. So now I'm going to assume 3 to the k odd. And you can talk about more about what that means if you want to start talking about the definition of odd right now. You could do that. I'm going to move on to the next part though, which is inductive step. And so now I'm going to talk about what it is that I want. So I want to show that 3 to the k plus 1 is odd. Well, something that I might notice is that 3 to the k plus 1 equals 3 times 3 to the k. Interesting, okay. So this isn't a want, this is, right? I know that, but I'm just starting with it. All right, so now I'm going to say consider 3 to the k plus 1. All right, so now I'm going to use this. So 3 times 3 to the k, okay. So maybe I should change what I have in my want. Maybe I should be more specific. What does it mean for 3 to the k plus 1 to be odd? Well, it needs to equal 2 times an integer. Well, we usually use k, so let's use something else. Let's use cursive L. No, that looks too much like a number. How about m? 2m plus 1 for some m in the integers. Okay. Oh, I left that out up here. For k and the naturals. You want to be specific, very particular. Okay, so let's go back. So what do we know? We know that 3 to the k is even. So I know that this is 2, oh my gosh, I'm running out of letters. How about p? 1, since for p, in the integers. Okay, so I'm about to introduce a different way of writing proofs that I think I've shown. So sometimes you're writing a bunch of computations, but along the way you want to explain why you're doing those computations. So off to the right-hand side is typically where I like to do it. I'll just write some statements. So P is in Z. I want to assume that, okay? And then I know that this is true. Here, let me write it neater. P and Z. Since 3 to the k odd. Okay, so this is not really part of the line. It's just me justifying what's happening in the line. I guess the P and Z is part of the line, but then I'm justifying why I'm saying this, why I'm allowed to do that. And you kind of want that devil's advocate in the back of your head being like, well, why can you do that? Is that a jump? Like, what is that letter? You know, you just want to keep having that discussion with yourself. Okay, so why don't I distribute? Okay. So I want it to look like this. So maybe I won't meld the 3 and the 2 together. Maybe I'll keep the 2 and put the 3 with the p. Okay, so now I have that 2 times an integer part, but I don't have the 1 part. Oh, well, we did this before with 3. I can rewrite this like this. So 3p plus 2 plus 1. Okay, so now I'm just going to combine these two things together. Okay, cool. Okay, therefore, since p is an integer, then 3p plus 1 is an integer. So 3 to the k plus 1 is odd by definition of odd. Okay, so am I done yet? I hope you said no, because I still have to write my conclusion here. So another thing you could have done that would have been a lot easier than this, but I just wanted to demonstrate some more thought process and stuff, is odd times odd is odd. So you could have just done that. You could have bypassed a lot of this stuff, but that's okay. Therefore, by induction, 3 to the n odd for all n in naturals. Woohoo! Cool. Okay, so now we're going to prove that n to the n is greater than or equal to the n factorial for all n in the naturals union 0. So if anyone needs a reminder of factorial, it just means n times n minus 1 times n minus 2 forever and ever and ever until you get to times 1. Okay, so it's that multiplication. Okay, so how do we do this? In 3 steps. If you're feeling confident, you could try this one on your own. You could pause me. All right, base case. Well, now my base case is not 1, it's going to be 0. Okay, so n equals 0. So here's where sometimes people get caught up, and they'll write 0 to the 0 greater than or equal to 0 factorial. But that is technically you assuming that it's already true, what you're trying to prove. So what you want to do is you want to say n to the n equals 0 to the 0, which is 1. And then 0 factorial, fun fact, is 1. So 0 factorial 1, well, 1 is greater than or equal to 1, so we're done. Right? Because it's equal. Great. Inductive hypothesis. So I'll be shortening them. You don't have to, but. All right, so now I want to assume for some k. So assume k to the k greater than or equal to k factorial for some k in the naturals or 0. Okay. All right, so now our inductive step. Let's talk about what it is that I want. I want to show, so here's where it really helps, this whole wanting thing, because sometimes this can be really hard to picture in your head unless you actually write it out. So for me personally, I'm going to start on this side. Okay. So I'm going to say consider k plus 1 factorial. So now I want to try to manipulate this a little bit so that I get something that I know about. So what do I know about with factorials? I know k factorial, sorry. So I know k factorial. So I can actually write this as k plus 1 times k factorial. Okay, so these two things are equal. So now I get to use my inductive hypothesis and say that this is less than or equal to k to the k. So, okay, so we need to be careful here. We're assuming that k to the k is bigger than or equal to k factorial. So if we replace k factorial with k to the k, are we making our statement bigger than or equal to that, or smaller than or equal to, less than or equal to? So the reason why we need to be careful with this is, let's say k plus 1 was negative for some reason, and then k factorial was positive. So if we multiply a negative thing by something larger that's still positive, then we're going to make our multiplication more negative, so it's smaller, right? So we just need to be careful. In a second, I'm about to write that why we know we're okay with doing this is because k plus 1 is in the naturals, so that means it's positive, and that k factorial is in the naturals, which means that it's positive. Okay? So why we're able to know that is even if k is 0, 0 plus 1 is in the naturals, and 0 factorial is 1, so that's in the naturals. So we're all set there. So because both of our elements are positive that we're multiplying, if I change one of the positive elements to bigger, then our whole multiplication is bigger. All right, let's try distributing maybe. So now I have k to the k plus 1 plus k to the k. Oh boy. Well, okay, well, since k is... Okay, so I got stuck here. Full disclosure, I got stuck here because I was like, well, wait a second, like if I change this or something, like how am I going to get what it is that I want, which is this. So what I'm going to do is I'm going to actually erase this line and I'm going to change my trajectory. So I already have this as k plus 1. I'm happy with that. What would make this perfect is if this was k plus 1 to the kth power. Because then I get, when I multiply them together, I get them to the power of k plus 1. So we need to really think about that though before we do it. So if we do that, if we do k plus 1, that could be bigger than or equal to what we already had. So for example, if k was 0, then it would be 0 to the 0, which would be 1. Okay, but if we did k plus 1, that would be 1 to the 0th, which is just 1. So those would be equal, but in pretty much any other scenario, it's going to be bigger, right? So like 2, let's say. So if k is 2 squared, that's going to be smaller than 3 squared. Okay, so I get to say here that that's greater than or equal to, and that's okay for me to say because all I want to show is that this is greater than or equal to this. Okay, I don't need that it's equal to this part right here. All right, I just need that it's bigger than what I already wrote over here. Okay, bigger than or equal to k plus 1 to the kth power. Okay, so now we multiply those together, and what do we get? We get the magic. Woohoo! Okay, so if you want a nice exercise, you could try it the other way around. Sorry, I don't know where my video just ended, but I'm almost done. So now I just want to say, therefore, by induction, n to the n is greater than or equal to n factorial for all n in the naturals, union with the set containing 0. Woohoo!